The two tests we did were the vertical jump test and then the 20-meter sprint test. This is because they're both relevant to basketball. The ideal methods of both the vertical jump test and the 20-meter sprint test are by far the most accurate, precise, and valid way to perform the tests. However, they both have their negatives, particularly in terms of accessibility. Firstly, the vertical jump test would be best performed and tested using force plates. The force plates work by measuring the ground reaction force of the performer. Before the participant performs their jump attempts, the researcher must calibrate the equipment by turning it on, setting it to 0, and checking the plates are level prior to weighing the participant and setting it to 0 again. The force plates can take up to 1,000 readings per second of the force produced by the participant, eventually equating to their total vertical jump score. Whilst doing this, the force plates can measure the amount of force being produced by the participant at each stage of the jump, which will also enable the researcher to see where the weaknesses and strengths of the participant are, meaning it could be extremely useful to elite athletes in particular to help them improve. Finally, the main problem with the force plates is their accessibility to the general population. The reason for this is because they are so costly, and anyone who wants to use them will tend to have to pay for a session in the lab, which is also expensive. The force plates also require a lot of knowledge and experience in order to use them safely and properly to get the most accurate result possible. And then for the 20-meter sprint test, the ideal method is to use light gates and high-speed cameras. Light gates are digital sensors that have only two settings, on and off. This means that when the sensor detects something going through them and break the light beam, as soon as the light beam is broken, it will record the time from the start to the next gate at the end or wherever it is placed along the distance. The ideal way to set it up for the 20-meter sprint test would be to have a light gate every 5 meters, so we're still able to get the split times for each 5 meters as well as the whole time for the 20 meters. Another way to make this method even better is to use cameras. 2D and 3D Vicon cameras can be used to analyze the movement of the participant in a higher level of detail. Vicon cameras have little motion tabs that get placed all over the joints of the performer and will allow the extra analysis of their movement. The software that can be used to help analyze the movement will be either Quintex software or Dartfish. The reason you could then use high-speed cameras is because they can take up to 1,000 frames per second, meaning it captures every minor detail of the movement. You're also able to adjust the shutter speed at different speeds for it to take photos faster and slower depending on the speed of it is set. To do this, the whole physical camera setup is crucial to be able to get all the angles. This process is called triangulation. To do this properly, all the cameras must be set up perfectly, including making sure there is no tilt on the camera by using the spirit levels provided on the tripods. In order to catch all the motion, you may need to pan the camera whilst the participant is performing the motion. To get it all perfect, it is necessary to have a few practice run-throughs of the test to make sure everything works and is good as it can be. On the negative side of things, there is a chance of perspective error because the camera setup might miss something due to them being set up in a certain way. An example of this would be the measurement of an angle may be different due to where the cameras are set up. Similarly to the force plates, this setup is extremely expensive and only labs tend to have access to this equipment or level of setup. On top of this, a huge amount of knowledge is required to carry out this test to its maximum potential. Due to limitations of the preferred ideal methods, we had to produce another way of doing it whilst maintaining as much accuracy as possible under the circumstances. Therefore, the way we chose to do the tests, starting with the 20-meter sprint test, we firstly set up five cones on the court, one at the start point, and then the rest every 5 meters until the finishing point at 20 meters. The way that we would time each participant would be with a timer standing at the halfway point, saying on your marks, get set, go for the participant, at which point they will then start the stopwatch. The timer will then press the lap on the stopwatch every time the participant gets to a cone, which will then say the split time between the cones and then the previous one. Meaning that at the end when the timer presses a stop on the stopwatch, it will have the participants' full 20-meter time as well as their split times for each 5 meters. The primary problem with doing the timing in this way is the fact that it leaves space for human error, meaning that it most likely will not be 100% accurate. However, it is as accurate as we can possibly do it. Each participant did 3 20-meter sprints to make sure that we maintained the best accuracy and validity we could. In terms of vertical jump test, again, due to limitations, we were not able to use a force plate. Instead of using force plates, we used a vertical jump tachymat, which is still accurate because it is still in relation to the height of the participant, and we weighed each participant too, so we should measure the force, so we can measure the force they're creating. The participant will have a belt around their waist with a string attached to it that they will have to then wind up to the correct length where it is completely straight from the floor to their hips. When they are standing on the mat, they will then perform their jump. They did 3 jumps each, and we took the best jump as their result. The positive about this method is that it eliminates most of the human error that can be involved with this method. However, there is still a slight chance a participant may not wind the string up properly, but this is not a frequent issue. Now, in terms of results for the tests, the 3 graphs for each player show the results of the 20-meter sprint test on different components with the components being distance time, velocity time, and distance and acceleration time shown on graphs. The model player's distance time will show. The model player's distance time graph shows that they took a little long to get moving fast for the first 5 meters of the 20 meters, and then for the last 15 meters they were much quicker and therefore covered more distance in a shorter amount of time. In terms of numbers, the first 5 meters were covered in 2 seconds, whereas the last 15 meters were covered in only 1.6 seconds, which is evidence of the fact that they were quicker after they reached the 5-meter mark. The velocity time graph for the model player presents the speeds the athlete was going at and what rate they were running at. The graph shows that for the first 2 seconds, the model athlete's top speed was 3 meters per second in comparison to the rest of the 20-meter sprint, where the fastest speed they reached was 25 meters per second. However, this may not have been accurate because that is extremely fast, but it was only for a split second, so they may have reached those speeds. The final graph for the model player is the acceleration time graph, which shows whether the athlete was accelerating and if so, at what rate. The graph shows that the athlete maintained the same acceleration rate for the first 2 seconds before they were able to fully accelerate. The faster rate of acceleration was 5 meters per second squared. The athlete then decelerated to 1.2 meters per second squared, which is part of the reason why their time perhaps was slower than it could have been, since they slowed down before the end of the 20 meters. For the weaker player, they also have the same measurements presented into graphs. Starting off with the distance time graph, they covered the first 5 meters in 2.2 seconds, when they were then able to cover the next 15 meters in a further 2.2 seconds. This clearly shows that the athlete was much faster as the distance progressed on. In terms of distance covered, due to how much more distance they were covering in the same amount of time, this shows that they were faster. The second graph of the weaker player is the velocity time graph, which shows that the athlete had an eventual steady progression as the 20 meters went on. For the first 2 seconds, they were traveling at 2 meters per second until they increased the amount of meters they were covering, when they reached 6 meters per second and eventually 10 meters per second at their fastest point of the test, which happened to be their end, when they went beyond 4 seconds for the time, finishing at 4.2 seconds for the 20 meters. Finally, the acceleration time graph presents the data for the weaker athlete and their acceleration rate. For the first 2.1 seconds of the test, the athlete was accelerating at a rate of 1 meter per second squared until they accelerated again to 5 meters per second squared 3 seconds into the sprint, before decelerating down to 1.2 meters per second squared. Finally, the athlete accelerated to the end, where they then reached an acceleration rate of 5.9 meters per second squared. This chart shows a comparison between the 20-meter sprint times with 4 different performers. These 4 performers were my performer, an NBA elite athlete, the group average, and the other is another player similar to my performer who got the best time in their group. The NBA elite player finished in a time of 2.4 seconds at their 20-meter time, making them the fastest out of the 4, which is to be expected. The next fastest was 3.25 seconds and was run by the better player in the group of participants. The group average time for the 20-meter sprint test was 3.7 seconds, which is almost the benchmark in terms of all performers in the group when we wanted to hit that mark. My performer ended up running a time of 4.8 seconds, which means they were the slowest out of the four. However, there are reasons that could be the cause of this. The first of which being that is because the amount of linear motion the participants are able to generate. For example, the NBA Elite performer will most likely be able to generate the most amount of horizontal direction, meaning they are able to run faster. Another reason could be down to the technique of the different participants and how much running training they have actually done. Then the final main reason for this could be the fact that there was less room for error in the NBA Elite players' time, meaning that they may also have had better conditions to run in. The time of the sprint will also be affected by the stability of the participant and where they are able to get their centre of mass, because if it is not balanced, then they may not be able to run as fast due to their posture. This bar chart shows the results from the vertical jump test in comparison. Again, the highest jump was from the NBA Elite player, which was to be expected again, with a jump of 96 centimetres in comparison to the best jump in the group of participants again, 72 centimetres, which is a fair difference. Compared to normative data, the 72 centimetre jump would be classified as excellent in comparison to the general population. The group average for the vertical jump test is 42 centimetres, which would be the average on most normative data in comparison to the general population again. My performer's highest jump was 23 centimetres, which is low in comparison to the group average, which means there could be various reasons of which this is the case. First of which being peak power. The peak power of the participants is important to consider when testing for vertical jump, because the higher the peak power they have, the greater chance they have of jumping high, because the primary component of fitness that vertical jump tests is power. Another reason for this could be that they were not able to use force plates in our tests because of the limitations, and the NBA Elite player would most likely have been able to, which means that they were using higher equipment. The final chart shows the data collected from the peak power calculation with the vertical jump test results as well. Peak power is the maximum amount of power generated that can be converted into energy the participants can use to create vertical force. The NBA Elite player generated 8,300 watts of power in their vertical jump test, which is extremely high, which is most likely a big part of the reasoning behind them being able to jump so high. My performer turned out getting the best score in the group of participants with 5,650 watts, which is much less than the NBA Elite player, but also good for their age and in comparison to the rest of the general population and group of participants. The peak power of an athlete is a big factor in vertical jump, and peak power is tested using the force plates. It will then show where that peak power is being generated and created from and how it is done, instead of just showing the result of the peak power. Peak power is measured against your weight, meaning it compares your weight to how much force you can exert and then calculates the peak power based on that. There are both advantages and disadvantages of a numerical model. The advantages of the numerical model are that it uses numerical values instead of lengthy explanations to present the data. This means that people will be able to understand it and will be able to clearly see that the data is presented in graphs and other methods instead of using different ways of presenting the data. Another benefit of numerical models are that they state the basic facts of the situation and the scenario. For example, the numerical model can state the simple thing that you have to do without going into too much confusion. The numerical model is easy to use for comparisons to other models in terms of the basic statements they make. However, they do not compare and state why this is the case. In terms of disadvantages, a numerical model for the first one is the fact that there's no context to the scenario, which could be the bad thing, because, for example, numerical model will say that you should do something and simply show how to do it, but it would not say when to use a certain technique and when it is most effective. Another disadvantage of a numerical model is that to test athletes, it can test athletes properly, but it often requires to use high-tech equipment and also have experience in the field, meaning that it can be inaccessible. This links to the final disadvantage of being costly. Whilst the simple numerical models are free to access, to test the performers to enhance the ability to compare their ability against other numerical models and other athletes, it can be very expensive to do.